In this video, we're going to look at various practical skills that you will need for your GCSE in physics. We're going to start by looking at the concept of proportionality. A linear relationship between two variables can be described with the equation y equals mx plus c, where one of the variables we plot on the y-axis, another variable we plot on the x-axis. The constant gradient is m, and the constant c is the y-intercept. Often we plot the independent variable on the x-axis and the dependent variable on the y-axis, and I will talk more about those a little bit later in this video. If the relationship produces a graph that passes through the origin, then the y-intercept is 0. This type of relationship is called directly proportional, just proportional for short, they mean the same thing. The variable on the y-axis is directly proportional to the variable on the x-axis if m, the gradient on this relationship, is constant. One way to write proportionalities is to use this proportionality symbol. It looks a bit like a fish. Y is proportional to x. Now we can turn any proportionality into an equation by replacing the proportionality symbol with an equal sign and a constant. And I'm just going to use k here for any old constant. And this works in all sorts of situations. Force is proportional to acceleration. That's Newton's second law, but it only works when we've got constant mass. Let's replace the proportionality sign with a constant. In this case, mass. A charge that flows through a wire is proportional to the time that we watch that wire for. And we could say that is true if the current is constant. So our constant of proportionality there is current. The energy transferred by some appliance is proportional to how long that appliance is used for. And that's true if the power of the appliance is constant. These equations probably look familiar to you. They're from the list of 23 equations that you have to memorize. And almost all physics equations that you'll meet are in this form, y equals mx plus c, or in this form where c is equal to 0. There are some exceptions, like the equation for kinetic energy, but there are ways to make that equation in the form y equals mx plus c as well. So how do we use proportionality? Well, let's just take this last example of energy being proportional to time. Let's suppose we have some appliance that transfers 20 joules of energy in 60 seconds. And let's imagine that we want to know how much energy is transferred in 90 seconds. Well, what we can say is that energy is proportional to time, and therefore the constant of proportionality in this case is power. We can calculate the power from the first example, which will be the energy divided by time, the energy transfer divided by the time, 20 joules divided by 60 seconds, which is about a third of a joule per second. And then we can use this in the second case. So the energy transferred in 90 seconds is going to be equal to the same constant we had last time, multiplied by our new time, 90 seconds. And that's 30 joules. We didn't have to guess at any point, we just used these equations. We calculated what the constant of proportionality was, and then we solved for it. Let's use a different example. In this example, 13 doodads produce 18 whatsits in 3 hours. So how many whatsits are produced in 3 hours? By 10 doodads. Well, let's write down our expression. The number of doodads is proportional to the number of whatsits produced. It's the same amount of time. So we have a constant of proportionality, let's just call it k, which we can solve for the first case. K is going to equal the number of doodads divided by the number of whatsits. And we can plug our numbers in. 13 doodads producing 18 whatsits. That's 0.72 doodads per whatsit. And now we use the equation to solve for the second case. How many whatsits? So that means we need whatsits to be the subject, and that's going to be the number of doodads divided by the constant of proportionality. We've just rearranged this equation to get whatsits as the subject. 10 doodads divided by 0.72 doodads per whatsit is about 13.8 whatsits. The independent variable is usually plotted on the x-axis, and the dependent variable is usually plotted on the y-axis for a graph. So we need to define these variables and know how to identify them in a particular investigation. The independent variable is how you impose your will on the situation. It's what you choose to do, the one you have a direct impact on. The dependent variable is how the universe responds to that decision. It's what changes as a result of your choice to impose your will on the situation. Your change of independent variable will have an impact somehow, and you can measure that impact. That's the dependent variable. The control variable is perhaps a little bit trickier. These are things that you could have changed and chose not to. And importantly, these are things that would have impacted the experiment in some way if you had changed them. Now, it's best to understand these variables with examples. So let's imagine that you are investigating the braking distance of a vehicle and how it depends on the mass of the vehicle. So here's our investigation written out in words. And the thing we can choose to change is the mass. We can't impose our will directly on the braking distance of a vehicle, but we can change the mass of a vehicle. The braking distance will be decided by the universe. There's various physics that goes into what decides what that braking distance is. We can measure what that result is, what the braking distance is. And then there are things we can choose to change. We can, for example, change the speed of the vehicle. But doing so would affect the braking distance, so perhaps we choose to keep that the same. That makes it a control variable. We could change the road surface, the condition of the road surface, the condition of the tyres, the condition of the brake pads and brake discs. All these things can affect the braking distance, so we choose to keep them the same. Those are control variables. The colour of the car we could choose to change, but it's not going to have an effect on the braking distance, so that's not actually a control variable. And be careful, don't just say keep the car the same. That's a little bit vague. We want to talk about physical properties of the car that we choose to keep the same. I could pick loads more examples, but you're going to get plenty of practice at that. So let's move on to errors. Errors are not mistakes. Errors are present in any investigation you do. Let's suppose I measured the diameter in 6 different places and got these diameters that you can see here. The mean is straightforward to calculate. We add these values together and then divide by how many we've got, which in this case is 6. When you do that calculation, you get 0.658 centimeters and a little bit more as well. But how much confidence do I have in that number? What's the error of that number? And we record errors by writing down an uncertainty in that value. So how much uncertainty is there in this measurement? Well, the way we calculate uncertainties in a very quick and easy way is to take half of the range of the values that are measured. So the largest value that's measured is 0.67 centimeters. And the lowest value that's measured is 0.64 centimeters. So our uncertainty is going to be half of the range. That's half of 0.67 minus 0.64 centimeters. That's 0.015 centimeters. And what we are saying is this value of the diameter could be that much higher or that much lower. That's the uncertainty in that measurement. And we would write this down as 0.658 plus or minus 0.015, and these are centimeters. Now, Isaac Physics won't let you put in numbers quite like this. It breaks it down into different parts, so don't worry about looking for that symbol on your keyboard. But that's how you could write out this. At GCSE level, we'll take the uncertainty to 2 significant figures. And then you have to choose a sensible precision for your mean. It's sensible to have the same number of decimal places for the mean as it is for the uncertainty. And of course, don't forget the unit at the end. Now, I was measuring a bunch of diameters then to 0.01 centimeters resolution. How could I do that? Well, there are 2 instruments that you can use to measure distances with more precision than you can measure them with a ruler. A ruler has a resolution of 1 millimeter. Vernier calipers have a resolution of 1/10 of a millimeter, and micrometers have a resolution of 1/100th of a millimeter. Now, I'm not going to go into the mechanical operation of these instruments right now, but I am going to show you how to read from the scales, starting with the micrometer scale. So here is a micrometer scale. As you can see, I can change the value on the micrometer scale to be whatever I want. The scale has 2 parts to it. There's the main scale, which you can see here, and there's the micrometer scale part, which you can see here. The main scale is along the main shaft of the micrometer, and there's a line running down the middle. There are numbers on one side of the scale. Those are millimeters. And in this micrometer, you can see that every half a millimeter, there's a notch on the other side of the scale. When you close the micrometer, this edge of the part that rotates is up against the 0. And as you open it, this part moves to the right. As it moves past the half a millimeter notch here, it means the distance is half a millimeter. And so we go half a millimeter, 1, 1.5, 2, 2.5, 3, 3.5, 4, 4.5, 5, and so on. So right now we know the distance measured by this micrometer is more than 12 millimeters. And we can work out how much more than 12 millimeters. This part of the scale, the micrometer scale, measures hundredths of a millimeter. So right now you can see it is on 40, 41, 42, 43 hundredths of a millimeter. You line up the central line down the middle of the main scale with the notch on the micrometer scale to find how many hundredths of a millimeter. So altogether this is 12 millimeters plus 43 hundredths of a millimeter. That's 12.43 millimeters. Here's another example. And as we walk along, we see we've got 0.5, 1, 1.5, 2, 2.5, 3, all the way up to here. 5, 6, 7, 8, 9.5. So this is more than 9.5 millimeters. More than 9.5 millimeters. But how much more? Well, the central line down the middle of the main scale lines up with the 21st notch on the micrometer scale. That's 21 hundredths of a millimeter, or 0.21 millimeters. So this is going to be 9.5 plus 0.21, 9.71 millimeters. Here's another one. Now let's be careful with this one. We can see that the line here has gone past the 11, 12, the 13th millimeter notch. So this is more than 13 millimeters. But how much more? And you can see that the central line lines up with a 7. It does not mean that this is 13.7 millimeters, because this scale is hundredths of a millimeter. So that is 13 plus 7 hundredths of a millimeter. That's 13.07 millimeters. Just watch out for that. And this is another time where you should be careful. If you look here, you can see 5, 6, 7, 8, 9 full notches. And on a real micrometer, you'll probably be able to see the 10th notch as well. So you might think to yourself, this is 10 plus whatever else there is on the micrometer scale. If you look on the micrometer scale, you'll see the line through the middle of the main scale lines up with the 49 hundredths of a millimeter notch. If this was 10 plus 49 hundredths of a millimeter, that would be almost at the next half millimeter notch, wouldn't it? But clearly it's not. We're halfway between two half millimeter notches. This is clearly very, very close to 10 millimeters. So when you're close to 0 on the micrometer scale, on the hundredths of a millimeter scale, then you have to be careful. You will see the 10th millimeter notch, but we're not quite there yet. We are 1/100th of a millimeter less than 10 millimeters. So this is 9.99 millimeters. Well, you'll get lots of practice using micrometer scales. Let's move on to vernier scales. This is a vernier scale. And on a vernier scale, there are two parts. There's the main scale on the bottom, and there's the vernier part that moves and slides along the main scale. And you'll notice, if you look closely, that on the vernier scale, there are 10 notches that fit into the space of 9 notches on the main scale. That's how these vernier scales work. Now, similar to with a micrometer, you can start with a number of millimeters. Look at this left-hand side of the vernier scale. It has just gone past the 7 millimeter notch. So we know that the distance measured by this vernier scale is just a bit more than 7 millimeters. But how much more? And that's where you use the vernier part. You line up the line on the vernier scale with a line on the main scale. And if you look, there's only one line that actually lines up, and that's this line here. That means that this is 0, 1, 1/10th of a millimeter more than 7. This tells you how many tenths of a millimeter. So this is 7.1 millimeters. Here's another example. You can see the line on the left has gone past the 2mm notch, and on the vernier part you can see that the second notch, 0, 1, 2, the second notch is the one that lines up. So because it's the second vernier notch, that's 2/10 of a millimeter. So this is 2.2 millimeters. Let's do this one. You can see the left-hand part has gone past 5 millimeters, so it's more than 5 millimeters. But how much more? Well, let's find lines that line up. These do. And that is the 0, 1, 2, 3, 4, 5, 6, 7, 8. The 8th notch on the vernier scale that lines up with the main scale. That means that it is 8/10 of a millimeter more than 5 millimeters. So that's that's 5.8 millimeters. The only time you have to be careful is when it looks like there are two lines that line up, like this, and then you use the one on the left. This is exactly 4 millimeters, but you would write 4.0 millimeters. So have a go at all those questions and good luck to you.